Okay, here's the recording in progress. So, start. All right, so welcome back. Hope you had a nice 3-day weekend. We only have 4 weeks left, one of which is next week is short, so we don't have that much time left for the class at all. So we have this week, next week, which includes 2 days off for Thanksgiving, and then before we know it, we're done. Okay, and you should have gotten an email reply back from me on the most recent quiz. And I emailed, or rather I sent on Canvas announcements the video. So if you didn't get a reply back from me, let me know. Okay, so we're doing our tests for convergence and divergence. I'm already up to 11.6. I wasn't scheduled to do 11.6 until tomorrow, so it looks like I'm a little bit ahead. So we'll see how it goes. Okay. So 11.6, we are here. Heads up for 11.7. 11.7 is not really even a new section. It's a review section. So 11.7 is a review of 11.1 through 11.6. So it's not even new. Okay, so that's just going to be, here's a series. You decide, should I do the integral test, ratio test, root test, test for divergence, and so on. Okay. Okay, so the biggie that we've been talking about is the ratio test, and we'll use this quite a bit from here on out. Ratio test, page 739. Okay. You take the ratio and absolute value of a sub n plus 1 to a sub n. If you get a limit and it's less than 1, the series is absolutely convergent and therefore convergent. If the ratio is bigger than 1, including infinity, the series is divergent. If the ratio is equal to 1, the ratio test is inconclusive. We can't tell. The idea is that the series is almost geometric. It may not be geometric, but it's almost geometric. And you might recall for a geometric series, if the common ratio was bigger than 1, the series diverges. If the common ratio was less than 1, the series converges, right? And the root test, we have very few problems with the root test. Now, on the quiz, some of you actually did the root test for the last problem on the quiz. I accepted it, even though that wasn't the idea behind it. But yes, the root test would have been easier. Okay. If you notice, it's pretty easy to take the nth root of the series in absolute value. Then similarly, it's quote unquote almost geometric. Okay. So if the limit is n approaching infinity of the nth root of absolute value of a sub n is L and it's less than 1, notice the conclusion is very similar to the ratio test. So less than 1, absolutely convergent and therefore convergent. Greater than 1 or infinity, series is divergent. And if the ratio is exactly 1, the root test is inconclusive. And by the way, also the root test is inconclusive if the limit doesn't exist. Same for the ratio test, then the limit doesn't exist. Here's an example of the root test, example 6. Okay, it looks like it's pretty easy to take the nth root, right? So you take the nth root. Sorry, I can't point it out because I don't have any more hands. I have 2 hands holding up the book. But if you take the nth root, you just drop that exponent. Then you have 2n plus 3 over 3n plus 2, which converges to 2/3. 2/3 is less than 1. So in the long run, I might be able to just barely squeeze this by. In the long run, this looks like 2/3 to the nth power. And we know 2/3 to the nth power is a convergent geometric series. Okay, so the series is absolutely convergent and therefore convergent by the root test. Okay, we have a few problems with the root test, but most of the time we'll be doing the ratio test in this section. Okay, so let's get back to where we were. We did some last time, and we'll do many more. Okay, so here is 9 star. It's not in the book. It was in the previous version, but it's good to look at anyway. Summation n equals 1 to infinity, -1 to the n, 1.1 to the n over n to the 4th. Okay, so most of the time we'll do the ratio test. So you write absolute value of a sub n plus 1 over a sub n. Okay, now once you see that, you can ignore the -1 to the n or n plus 1 or n minus 1, because again, -1 to the whatever, it's either going to be 1 or -1, right? Like -1 to the 0 is 1, -1 to the first is -1, -1 squared is 1, -1 cubed is -1. It just goes 1, -1, 1, negative. But if you have the bars, they're all 1. So it's all 1, just ignore it. Okay, and now our shortcut for a sub n plus 1 divided by a sub n. So just like a function, you put n plus 1 here and here, right? So 1.1 to the n plus 1 divided by n plus 1 to the fourth. And then instead of dividing by a sub n, it looked very clumsy, right? You got a fraction on top of another fraction. Just immediately flip the original. So I'm just going to go times, and notice I just flip it, n to the fourth over 1.1 to the n. So that's the way I'm going to be writing it from here on out. Okay, it's not that big of a jump. You're all in Calc 2, so your arithmetic is good. You know that when you divide by a fraction, you just immediately multiply by the reciprocal of the second fraction, right? So when we do stuff like this, generally, we will leave this orientation the same, put an n plus 1 there, put an n plus 1 there in parentheses, and then just flip the original. Okay. And then we will group like so. Okay, n to the fourth over n plus 1 to the fourth, that's like n over n plus 1 quantity to the fourth power. And then what is 1.1 to the n plus 1 divided by 1.1 to n? That's just 1.1, right? You subtract the exponents. Okay, and what does that approach as n approaches infinity? When the n gets big, this approaches 1, 1 to the fourth is 1. So this whole series approaches 1.1. That's bigger than 1. Therefore, the series is divergent by the ratio test. Okay, no abbreviation for ratio test. I don't accept RT. RT could be root test, and it's not that many letters. It's what, 9 letters. Okay, but you could put SD for series divergence. Okay, so this is the ratio test. We do a lot of problems involving the ratio test. Okay, 13, which I believe does match ours, yes. 10 to the n, all of this stuff. Okay, so write absolute value a sub n plus 1 over a sub n. Okay, so for a sub n plus 1, put an n plus 1 here, here, and here, all in parentheses. So it's 10 to the n plus 1, n plus 1 plus 1, 4 to the 2 parentheses n plus 1 plus 1. Now, technically, all of these should have parentheses, but you realize if I put an n plus 1 here, it's the same thing. You can just drop it. And likewise, if I put parentheses here, it's parentheses n plus 1 plus 1. That's still the same thing. But here it's crucial. You have to put parentheses. And then you go times, flip this. Just completely flip it. N plus 1, 4 to n plus 1 over 10 to the n. Okay. All right, this is 2n plus 2 plus 1. I'll rewrite it as 4 to 2n plus 3. Okay, now I'll group things that are alike. N plus 1 over n plus 2. That divided by that, 10. 10 to the n plus 1 minus n, 10 to the 1. Now about that divided by that, 4 to the 2n plus 1 minus parentheses 2n plus 3. That's 4 to the negative 2. 2n's drop out, right? Then I have 1 minus 3 is negative 2. 4 to the negative 2 is 116. Okay, and as n gets big, this ratio approaches 1. So this approaches 5/8 as n approaches infinity. 5/8 is less than 1. Therefore, dot, 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 series is absolutely convergent by the ratio test. Right, so in the long run, in super big N, this looks like a geometric series where you keep multiplying by 5/8. And if you keep multiplying by 5/8, you get a convergent geometric series. Not quite geometric, but it's quote unquote almost geometric. Okay, 17 star. Okay, I'm actually going to do 17, which was 19 in the old version, but it's okay. Summation n equals 2 to infinity. Okay. Side note, they start at 2. Can you tell what's wrong with 1? ln 1 is 0, so you'll be divided by 0. And does this start with a positive or negative? Because they're indexing beginning at 2, right? Negative 1 squared is positive 1. So it starts off with 1. So 1 over ln 2 minus 1 over ln 3 plus 1 over ln, and so on. Okay. All right, this looks like a giveaway for alternating series test. It's alternating. Terms decrease in absolute value, and they approach 0. So therefore, the series is convergent by the alternating series test. So it's definitely convergent But let's talk about absolute convergence or not. Okay, so is it absolutely convergent or conditionally convergent? So to find that out, we take the new series where all the terms are positive. In other words, the absolute value of a sub n of the terms. So summation absolute value of -1 to the n over ln n. Well, again, that just makes the numerator is all 1, right? Absolute value of 1 is 1. Absolute value of -1 is 1. So just summation of 1 over ln n. So what happens to summation 1 over ln n? Well, a nice comparison series is 1 over n, our famous harmonic series. Okay. Think back to graphs. Y equals x looks like this. Y equals ln x looks like this, right? So x is greater than ln x. This graph stays above this graph. Therefore, by the reciprocal rule, 1 over x is less than 1 over ln x, right? Or switching back to n, 1 over n is less than 1 over ln n. And what do I know about summation 1 over n? That diverges because it's the harmonic series. So the smaller series diverges. Right? Therefore, anything bigger than that, summation 1 over ln n, also diverges by the comparison test. Okay? So this would be the case of you're richer than a rich person. If you're richer than a rich person, you're rich, right? All right, so therefore 1 over ln n also diverges by the comparison test. So getting back to the original question, this series converges. But if I look at the absolute value, I'm shooting for absolute convergence, which really means absolute value convergence. Pretend it says a 1 over ln n, that diverges. So therefore, by definition, the series is conditionally convergent, CC. Okay. All right, now I'm actually going to do 17. It was 19. If you see this, it used to say 19. It's now 17 in our new edition. Okay, summation n equals 1 to infinity, cosine n pi over 3 over n factorial. Okay. Now, we've already seen n factorial before. 1 over n factorial, we thought converged, it does. But I've got this thing on top, and this is not alternating, by the way. The cosine, bounces up and down, positive, negative, between -1 and 1. Okay. But I'm going to aim for absolute convergence. Okay, so I'm going to look at summation of absolute value of a sub n. Okay. That way we will have only positive terms, and then maybe I can use a comparison test. So look at the absolute value of a sub n. Summation absolute value of cosine n pi over 3 divided by n factorial. Okay. And I know that absolute value of cosine there. Absolute value of cosine n pi over 3 is certainly less than or equal to 1. And then divide both sides by n factorial. Right. So in order to use a comparison test or limit comparison test, you might remember that you have to have series with only positive terms. This series was not only positive terms. It bounced. It's not alternating. It's not alternating either. But if I do the absolute value stuff, then that forces everything to be positive, right? So now I look at summation 1 over n factorial. Does that converge or diverge? Now we saw before that it did converge by the comparison test. Remember, we compared it to 1 over n squared. It was a little bit clumsy. Okay, it's a lot easier by the ratio test. Okay, so let me show you by the ratio test that this thing converges. So absolute value of a sub n plus 1 over a sub n. All right, so the way the game works again is for a sub n plus 1, just change this to n plus 1 in parentheses, 1 over n plus 1 factorial. Divided by the original now means times the flip. So just quickly multiply by the reciprocal of the original, n factorial over 1. Okay, and these ones don't do anything. And we've played this game before. N factorial divided by n plus 1 factorial. So are there more factors on the top or on the bottom, and how many more? Right? There's one more factor in the bottom, n plus 1. See, the top is 1 times 2 times 3, dot, 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 up to n. This is 1 times 2 times 3, dot, 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 times n plus 1. So everything's going to cancel out except for the n plus 1 in the bottom. Okay. And now as n approaches infinity, this expression approaches 0. Okay. So therefore, summation of 1 over n factorial is absolutely convergent by the ratio test. Right, so this series does converge, and now we have this comparison series, which is smaller than it, term by term of positive values. Okay, so therefore, the original series, this series, absolute value of cosine n pi over 3 divided by n factorial, also converges by the comparison test. Okay, so it's smaller than something which doesn't get big. Okay, you're poorer than a poor person, so to speak. Okay, if you're poorer than a poor person, you're also poor. Okay, this thing has a finite value. So how can something which is below it diverge? Below it, it doesn't. Okay, so therefore the original series is absolutely convergent by definition. Okay, we did the absolute values and we got convergent. Okay. Okay, problem number 19. Okay, it used to be 25. It's 19 now. By the way, this problem is to kind of show you how powerful, I guess, the factorial function is. I mean, you look at this, like, remember, n is getting big. Plug in a million. This is huge, right? If I plug in a million, this is huge. This is big, of course. And you're wondering, okay, you got both of these. These two are sort of ganging together, ganging up against this one. Let's just go ahead and see what happens in the long run, though, right? I mean, think of plugging in a number like 2. 2 to the 100, big. 100 squared, big. Divided by 2 factorial is only 2, right? And if I plug in like, I don't know, 3. 3 to the 100, real big. 100 cubed, big. 3 factorial is only 6. It looks like the top is winning. Believe it or not so in the long run. In the long run, this guy wins. Both of these combined, believe it or not. Okay, that's how strong, powerful the factorial is. It beats both of these combined in the long run. Anyway, how do we prove that? Ratio test. So here, put n plus 1. Here, put n plus 1. Here, put n plus 1. Divided by a sub n means times the flip. So flip this, n factorial is on top. These two guys come down. Okay, then I combine these two. That's n plus 1 over n to the 100th power. These two, 100 to the n plus 1 divided by 100 to the n. If you subtract, you have 100. And we just saw this, n factorial over n plus 1 factorial. Leaves me with n plus 1 on the bottom. What does that approach as n approaches infinity? That approaches 0. This is 1, right? For super big n, that's 1 times 100 over n plus 1. Okay. The bottom wins out. You would have to get fairly high up to tell, but I can't even show you by plugging in. But if you plug in 1,000 here and 1,000 here and 1,000 here, you can't really, most of us aren't that intuitive with these numbers, myself included, but the bottom wins. In the long run, the bottom will win. Okay. So the series is absolutely convergent by the ratio test. Okay. All right, so that's a ratio test. I do have some problems with the root test that I want to show you. Okay, so this was 21 in the old version. This is now 25. Yeah, 25. Okay, notice I got the lazy notation. Okay. So the root test. And you say, how do you know to use the root test? If it's pretty easy to take the nth root, right? Because if I take the nth root, then I just forget about that, right? So here we go. Nth root, absolute value. Strictly speaking, you need the absolute value. N squared plus 1 over 2n squared plus 1. So if I take the nth root of an nth power, you just drop this, n squared plus 1 over 2n squared plus 1. And this limit's going to be a half. right? Then quickly, you can see 1 drops into insignificance, and n squared over 2n squared is a half. But formally, you could do this, right? Limit n approaches infinity, use L'Hopital's rule. Infinity over infinity. Derivative of the top is 2n. Derivative of the bottom is 4n. That comes out to be 1/2, less than 1. So therefore, this series is absolutely convergent by the root test. Okay, so you may write S for series, AC absolutely convergent. We know it's not air conditioning, but do not use RT. That's ambiguous. RT might be root test, it might be ratio test. And I figured that's not that many letters. It's only what, 1, 2, 3, 4, 5, 6, 7, 8 letters. You can write out the whole thing. Okay, and here is 29, which was 23 in the old version, but yeah, 29 here. Okay, summation n equals 1 to infinity, 1 plus 1 over n to the n squared. Okay, so let's take the nth root of this thing. So nth root of 1 plus 1 over n to the n squared. It's a little bit clumsy. But remember, if I take the nth root, right? The nth root means raised to the 1 over n power. So I copy this, raised to the 1 over n. And now from algebra, if I have a power of a power, I multiply the power. So n squared times 1 over n is just n. You might have seen that limit in Calc 1, but I'll go over the proof of that. This actually comes out to be e. Limit as n approaches infinity of 1 plus 1 over n to the n is e. E is like 2.7. That's greater than 1. Therefore, the series diverges by the root test. Okay, this is e. I'll show that to you. Your Calc 1 teacher may have proved that this was e, but so little timeout, show you that this limit is e. So limit n approaches infinity of 1 plus 1 over n to the nth power. Okay, so let y equal this thing, 1 plus 1 over n to the n, which means we want the limit as n approaches infinity of y. I take the natural log of both sides, ln, ln, and once I have the ln, that n gets to come down. So ln y is n, ln 1 plus 1 over n to the 1. And multiplying by n is the same as dividing by 1 over n. And now when n gets big, this is infinity over infinity. If I have a super big number here, that approaches 0. And that would approach 1, and ln of 1 is 0. So that means L'Hopital's rule does apply. You might remember L'Hopital's rule, if you get 0 over 0, you take the derivative of the top, derivative of the bottom, and get the same limit. So the derivative of the bottom, I'm just calling 1 over n prime. I don't really need a derivative. What's the derivative of this? It's 1 over 1 plus 1 over n times the derivative of the inside, which is 1 over n prime. The 1 over n primes just cancel out. So I have this. So now when n gets big, this approaches 0. So I have 1 over 1 plus 0, which is 1. So that means I now have the limit as n approaches infinity of ln y. Remember, I took the ln of both sides. So limit as n approaches infinity of natural log of y is 1. To get rid of the ln, now I exponentiate both sides, put an e here and an e here, and the e and the ln can cancel out. So what I was looking for is limit n approaches infinity of y, which is e. Okay, all that to say that this limit is e. So getting back to over here, right? The limit was e, that's bigger than 1, so the series diverges by the root test. Okay. All right. A couple of problems at the end, 43. It says, for which of the following series is the ratio test inconclusive? That is, it fails to give a definite answer. Okay, so you're supposed to do the ratio test, even though you might know that it's already convergent or divergent by some other reason. Okay, so I'll show you A and B. Okay, summation 1 over n cubed. Now, I already know that this series converges by the p series rule. Remember p series, if the p, the power is greater than 1, the series converge. And if it was less than or equal to 1, the series diverge, right? If the exponent was exactly 1, that was the cutting edge of convergence or divergence, right? Summation of 1 over n diverge, that's our harmonic series. But if I put a number just above 1, like 1.001, this series would converge. But that's not the question. The question is, what happens when I do the ratio test? So a sub n plus 1 over a sub n in absolute value. So 1 over n plus 1 cubed divided by the original means times n cubed over 1. So I can rewrite this n over n plus 1 cubed, and that approaches 1 as n approaches infinity. Okay? So if the limit is 1, the ratio test fails. So we already know this series converges. You just can't tell that by the ratio test. So we have to try some other test. Doesn't work. B, however, was what? N over 2 to the n. 43b. So absolute value of a sub n plus 1 over a sub n. Okay. So the ratio test, put n plus 1 there, n plus 1 there, times the flip of this. Flip it, 2 to the n over n. And why did I have this funny circling here? N plus 1 over n is that. 2 to the n divided by 2 to the n plus 1, that's a half. Right? It's 2 to the n minus 1. You're left with 2 to the negative 1, or a half. And now when n gets big, that approaches 1, right? So this expression approaches a half as n approaches infinity. Half is less than 1. Therefore, the series is absolutely convergent by the ratio test. So in the long run, this behaves just like a geometric series where you keep multiplying by a half. Okay. And then we have a couple of pretty strange questions. Well, you have problem like 21 and 23. That's some strange factorial and factorial-like thing. Okay, I'm going to do, guess I have to call it 27 star, since it's not in the original version. Okay. The original went 1 times 3 times 5 times 2n minus 1 factorial, 2n minus 1 over 2n minus 1 factorial. This is kind of like the odd factorial. So if you look at 21, 1 times 3, 1 times 3 times 5, 1 times 3 times 5 times 7. It's not factorial, it's kind of like an odd factorial. You jump every 2. Okay. 23 is kind of like the even factorials. You skip all the odds, 2, 4, 6, all the way up to 2n. Okay. So I'll show you this one. So the original, when 1 times 3 times 5, 2n plus 1, 2n plus 1 factorial. Really messy, but you can still do the ratio test. So 1 times 3 times 5, 2 parentheses n plus 1 minus 1, 2 parentheses n plus 1 minus 1 factorial. This was the original flip. So if you want to see the original problem, just flip this. 1, 3, 5, 2n minus 1, 2n minus 1 factorial. Okay, now, this is 2n plus 2 minus 1, right? 2n plus 2 minus 1, so it's 2n plus 1 factorial. I can rewrite this as 1 times 3 times 5, Now, this is 2n plus 1. That means the factor just before it was 2n minus 1. These are all 2 apart. Okay, so if they're 2 apart, this is 2n plus 1. The one just before it is 2n minus 1. Now, all of these, cancel all of these, I have an extra 2n plus 1. Now look at these two. 2n minus 1 factorial, 2n plus 1 factorial. This has 2 more factors that this doesn't have. So what comes after 2n minus 1? 2n. And then 2n plus 1. Okay, so there's an extra 2n plus 1 on the top. The bottom's going to have 2 more factors, 2n plus 1 and 2n. This is 1 times 2 times 3 da, 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 times 2n minus 1 times 2n times 2n plus 1. Those last two that I said aren't with the original. All the others cancel out. And now these even cancel out. So ultimately, I have 1 over 2n. That approaches 0 as n approaches infinity. Okay, so therefore, the series is absolutely convergent by the ratio test. Okay, and last one I'll show you is 39. It was 31 in the old version, but 39. 39. The terms of a series are defined recursively by A1 is 2, A sub n plus 1 is blah, blah, blah. Determine whether the series converges or diverges. It's actually easier than you think. Because, now, I'll show you the book. They show me this. All you got to do is divide both sides by A sub n. Divide both sides by A sub n. It looks like this. And I can put the bars, which is required by the ratio test. You say the original didn't have any bars. Yeah, but if you plug in 1, 2, 3, 4, 5, these are always positive, right? So I can put it in. This definitely approaches 5/4 as n approaches infinity. 5/4 is bigger than 1. Therefore, the series diverges by the ratio test. So we have a divergent series in this case. All right. Okay, and I think I'm done for 11.6. So that was all I was going to do for now. And let's see schedule-wise. So tomorrow I'll start 11.7, which is not really a new section. I wasn't supposed to start 11.7 until it looks like Thursday the 18th. Again, I'm a couple of days ahead. The topic is strategy for testing series. There's no new stuff. It's just a review of old stuff. So it's nice and compact here. All the problems are on page 746. But you just kind of have to recall all the different rules that we have for convergence or divergence. So this would be more in line of something I might give on the exam, right? You have to pick the right test. Okay, does this look like it's a harmonic series or comparison test or integral test, right? That's the kind of thing that you're up against. And we'll start some of that tomorrow. Okay, but otherwise I'm done for today. So let me stop the share and check the chat. Otherwise we're finished. So anybody with a question, please? All right, so have a good day and we'll see you all next time. Okay, all right, bye everybody.
Thank you.
Thank you.